Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on electrochemical series. Now, I make this video after the last video, which was on electrochemical cells or what was it going to be on? Yeah, electrochemical cells, where I talk about the basics of what what a cell really looks like, electrochemical cell looks like, why it's done in that way, what it's representing, how is the current made using this type of cell method, the two processes that are happening in a cell, which is oxidation and reduction, the type of electrodes used, the basics of this topic, as well as half equations, reduction potentials, standard hydrogen electrodes, and it's things I went into in a very basic manner because this is the first time you're hearing it. So I couldn't really go and explain to you how to calculate cell potentials and the electrochemical series, how we deduce which reactions are going in the reaction of in the direction of reduction, and which are going in the direction of oxidation, which I'll be going through in this video. How to actually calculate, how we use that calculation to determine how the reactions are going to occur, which reactions are more likely than others, and what would that mean? What results would we expect out of that outcome? What would we expect to see at our electrode or our solution at the end of the day? And that's what I'm going to go through in this video. At the end of this, I said as I tried to say before, I wasn't able to give you a better example because I was trying to explain the basics of this. So I couldn't go and do examples of this question. But now, as I go, by the end of this video, I'll be going through a couple of exam-style questions. Now, would you be able to answer some of these exam-style questions? Probably not. And when I finish physical year 2, I will do some exam-style questions on this topic in particular. But I think the best way of me doing it is that I'll leave the option for if you do know how to answer these questions at the end. I'll leave a link in the description and I'll allow you to go look at them first. But if you are completely lost on this topic, I'll go through how to answer those exam-style questions at the very end. And yeah, I think that's enough of me talking, and I'll just go straight into the video. So, the electrochemical series. So, standard reduction potentials are listed in the electrochemical series. So, this is the electrochemical series table here. The electrochemical series. So, we list lots of half equations with their standard reduction potentials in a table called the electrochemical series, where the most negative potentials are the hardest reductions to do, or the easiest oxidations to do, at the top, and the standard hydrogen electrode potentials in the middle at 0 volts, and the easiest reductions to do are at the bottom. Now I want to make this clear. So this is the table that I was talking about. Now this isn't actually how it's represented, but it's just a way of you understanding the electrode potentials of certain types of elements. But this is a very, very numbed down, very basic, minuscule table compared to what the actual table looks like. The actual table is all the different types of electrode potentials of all the types of elements or ions that we would have, and how they would and how we can measure their reduction potentials. Now, I'm going to use example questions, which is actually a better way of showing how the table actually looks like. It looks more like this, which is a much better way of representing it, where you're seeing the type of reduction. For example, CO2 plus 2E minus goes to make 2Cl, goes to form 2 chloride ions, 2Cl minus ions in solution. And if we measure that type of a reduction potential, that's plus 1.36. This is a much better way of doing it because there's different forms of ions, reductions of chlorine that we could have. We could have a chloride ion, the different types of chloride ions. We could have just chlorine element being reduced. For example, we have, in this example here, we have both Fe3 plus and Fe2 plus being reduced, and they're both the same atom but different ions, right? And have different, and you can see they have very, very different types of reduction potentials. One is more likely to be reduced and one is more likely to be oxidized. You see, and so this is what the actual table has a long list of every single ion and every. Now you don't need to know in your exam they'll represent it like this because you only need to know the specific electrode potentials of the. You only need to know the specific electrode potentials of the question that they're giving you. So they'll give you the electrode potential of if they're emphasizing on a small group of ions, they'll just give you those group of ions to make it easier for you, which is great in a way it is. And but yeah, I want to just give you a heads up of what this represents, or what it is, and this is very useful for you to actually answer your question, whether it's working out the cell potential, or allowing you to understand which reaction is going to be more likely to be reduced, which one is more likely to be oxidized. Again, I'll go through how to answer that later on. Also, through this video, what those cell potential means, what it means for the overall reaction, right? But I'm gonna just go. Actually, I'll go through it right now. So calculating cell potentials, right? So we can use standard reduction potentials to calculate the standard cell potential, and this will allow us to predict the outcome of the reaction. Here, this is the most important part of calculating cell potential. It allows us. Oh, no, I'm not gonna rub it out. It allows us to predict the outcome of the reactions, right? Because if we know, yeah, I've got the equation here, right? But if we know what the cell potential is, whether or not it's positive or negative, tells us which one's going to be. Well, first we need to know which one's going to be going in the oxidation way and which one's going to be going in the reduction way. And that's something that I probably highlighted in my last video, but I can say it again. And once we know that, we can then that in itself is enough to tell us which way we're going through. But if you're uncertain about that, you can work out the cell potential, and that will determine whether or not the reaction is feasible, right? So you pick two half equations, which I'll go through it. I can go through an example at the end. Back to that question again, right? And we can decide which is happening as an oxidation and which is happening as a reduction. Now we subtract the standard reduction potential for the oxidation from the potential of the reduction. Now then the equation is this: the cell electro potential, or the standard cell potential, is the electro potential of reduction minus the electro potential of oxidation. Now that just depends. Now this is where you need to understand which one's being reduced. Now the one that's going to be more likely to be reduced is the more positive value, right? I said that in the previous video. Remember, I said the more positive your electro potential, the more likely is that reaction is to be oxidized in comparison to hydrogen, the reduction of hydrogen in comparison to the reduction of hydrogen ions. Yes, I was making sure there's hydrogen ions. Yeah. So you go back here. The more positive your value is, right, the more likely it is that your whatever you're reducing is more likely to be reduced in comparison to reduction of hydrogen ions, and the more negative it is, the more likely it is to be oxidized in comparison to reduction of hydrogen ions, or more it's less likely to be reduced in comparison to the reduction of hydrogen ions when it's more negative. So let's pick an example, because I think everyone thinks they have to have a positive value and a negative value. No, that's not what it has to be. It can be you can have two positive values here. But let's pick these two. Yeah, let's pick this two. I'm gonna just pick any random two, right? Yeah, go for these two here, right? Now, which one is more likely to be reduced and which one is more likely to be oxidized, right? Now I can tell you for certain right now, I'll just use my black pen, that this is more likely to be reduced than this, because it has a higher electrode potential. Not by much, only by 0.3, but still more likely, right? And also, by the way, as you can also tell, the higher the difference, the faster the rate of the reaction usually, and the more likely the reaction is more to happen. So it wouldn't be a very fast reaction, but it still would happen. It still would happen. The electron potential is higher. Now, how do you actually go about looking at this, right? We'd say that this reaction is more likely to go in the reduction pathway, because that's a higher electron reduction potential, right? So then that means that if one's being reduced, the other must be being oxidized. Therefore, this reaction is more likely to go in the oxidation pathway. So it's more likely to go in that way. We look at the the reactions, right? So we say the first thing we look at is the number of electrons, that they both have the same number of they both have the same number of electrons, so we don't have to times one by two times another by two. They're both balanced, right? So now we look at saying if we was to write this out as a full equation, how do I write this out as a full equation? The full equation would be Ag plus, so the one that's being reduced plus the one that's being oxidized, right? Now, you know what? I'll write them out as two. I'll write them out as two half equations, so it makes it even easier for you to see what I'm trying to talk about here, right? So let's say Ag plus the one we know that one is Ag plus as it is aqueous plus an electron goes to form Ag solid, right? And the other one is going to be going in the other way. So Fe2 plus aqueous is going to be oxidized to Fe3 plus an electron, or is it also aqueous? Now, if I was to write this as a full, remember what we said before, you can combine two half equations to make a full equation, given that the electrons are balanced. We both have one electron on either side, so you can just write them together. So Ag plus Fe2 plus, and now I should write the state of matter, but I'm just doing it here for, I'm just trying to save time. You already know what I mean. You obviously write your state symbol, your symbols that represent your state of matter, but you can see what I'm talking about here, right? Plus Ag, so Ag plus, right, plus Fe2 plus goes to form Ag plus Fe3 plus. You don't need to write, in a full equation, you don't need to write the number of electrons, because if I was writing the number of electrons, you would have an electron here, right, from this here, and an electron here from from the product side of here, and they just both cancel each other out. Now, in a reaction, this applies to anything else. If you have the same compound in the reactants and the products, you just cancel them out. I can just see it here. I can just cancel out. I don't need to think about it right now. But you just cancel them out. So if you have H2 on both sides of the equation, you just cancel them out, right? Okay. So hopefully that made sense. Yeah, I'm not going to just do that because I don't want to give people... I don't want to... When I actually do this question, you'll see, right? But there's some examples. I'm going to go through this one too quickly right now because I don't want to spend too much time going over this. But one final example here. Cells going through... Actually, yeah, I want you to do this one here. This one and... yeah, that. I want you to try and do that one then. So pause video now and try and do that. Okay, I assume you've paused the video and tried to do it. If you haven't, then you can just see it. But if you had no idea what to do there, that's fine. Right, I'm going to show you what this answer is. So I can see that, and because which one's more likely to be reduced? Obviously, we can see it's going this direction here. And by the way, if you already know how to answer this question, you want to go back to the content, you can just skip to that part of the video. Don't worry about this. But if you want to know about how to answer, because you can see that they don't have the same number of electrons here, right? So it's a bit different. So what we see here, so we say this, we don't have to always write the equation. I'm just writing out the equation for you to guys to get help. You won't get any marks extra for this, but just to give you an example of, just to help you understand what we're looking at here. Now, always write out your symbols to represent your state of matter, but I'm just doing this for the sake of you understanding how to answer this now. We know this is going to be Fe2 plus an electron. No, sorry, Fe2 plus goes to form Fe3 plus an electron. We just balance it out. If we want to get the same number of electrons here, just times this by 1, the top by 1, which is doing nothing really. I'll leave that as it is. But times this by 2. So it'll be 2 Fe2 plus, 2 Fe3 plus, and then 2 electrons, right? Now, the more you do these types of questions, the more easily you can see this. You don't have to spend much. You can do it all in one go. But I'm just trying to go every little part here. Now the electrons are balanced. We have it now. Cl2 plus 2Fe2 plus goes to form 2Fe3 plus plus 2Cl minus. Now hopefully you got that now. And yeah, that's that. Or let me just, if you didn't see that there. Good. Right. I promise I'll move on now. I know I talked way too much better, but I wanted you to kind of get it because that's so important to actually answer that question. All right. I had an example here, right? I had a perfect example. I had an example here, but it is what it is anyway. So, but when you're actually no, this is for the calculating the cell potential. So, magnesium and bromine here. So here we have two two reduction potentials. The standard reduction potential for Mg2 plus 2E minus goes to form magnesium solid. The electric potential for that is minus 2.37 volts. And the standard reduction potential of for Br2 plus 2E minus goes to Br2 plus 2E minus goes to form 2Br minus, AQS, and the electric potential for that is 1.07. Now, the magnesium potential is more negative, so we'll go down in the oxidation direction. So put this in white. This is more likely to go down this way. Wait, I mean, don't want to go do that. You can already see what I'm talking about anyway. But the magnesium reaction on the top right is more likely to go in the opposite, the left, from right to left. It's going to go in the oxidation pathway because that's a more negative reduction potential. So it's going to go in the oxidation direction. And henceforth vice versa for bromine, because bromine's potential is more positive, so the bromine will be reduced. And that's all it is. Magnesium is being oxidized, bromine is being reduced. That's why these reduction potentials are so important, because it tells us which directions is direction going in, and it tells us for certain. Well, actually, you know what? I'm gonna go through the rest of this and explain my other point here, right? But you can see here, magnesium being oxidized, bromine being reduced. The equation for this reaction between magnesium and bromine is here. It'll be, well, this is just me explaining how I got to that Mg plus Br2 goes from MgBr2. You should understand how they got to this reaction by how I explained it before a couple of seconds ago, right? But you can clearly just see here, the overall reaction is Mg solid plus Br2 goes to form MgBr2. The cell potential, right, is, we follow the equation, the electric potential of what's being reduced minus the electric potential of what's being oxidized. So it'll be 1.07 volts minus 2.37, and minusing and minus is just adding it together, right? And it's 3.44 volts. Now, what I was gonna say here, why I was saying that it's important to understand the electron potentials, I kind of brushed upon it before continue on here, but it's why it's important, because now this tells us that this reaction is feasible. If your electron potential, your overall electron cell potential is positive, it means the reaction is feasible. And think about it with this vice versa. If I told you that magnesium was the one that's being reduced here, I said, in fact, they give you questions like this. They say things like, why is it that it's less likely for magnesium to be reduced, or why is it less likely for bromide ions to oxidize? Yeah, why is it less likely for bromide ions to reduce Mg2 plus? And you can see here, right, that is, you can just, all you have to say here is that the electron potential for Br2 is greater than the electron potential for Mg2 plus, and so that's in itself, that's really enough. And say therefore, Br minus is more likely to so therefore Br2 is more likely to oxidize Mg solid compared to 2Br minus reducing Mg2 plus, right? But all I'm saying, if you can see here, if we imagine that was the case, right, where they were saying that Mg2 plus was the one that's going to be more likely to be reduced, we would be doing minus 2.37 minus 1.07, and that would get minus 3.44 volts. And if it's a negative, if our overall electron cell potential is negative, means the reaction is not feasible. So it is just all different ways of just emphasizing the point that this reaction isn't feasible because of this reason. So electron potential is also negative. Our individual electron potential don't follow the usual rule that we have. So therefore, it must go in this direction only. That's what I'm trying to emphasize. They probably didn't say it in the right way. What I'm trying to say is that if we said that this reaction is, magnesium is more likely to be reduced, and this is more likely to be oxidized, then our equation, if we did that as an equation, we'd get minus 2.3. Oh, damn it! You know what? I just do it here. Minus 2.37 minus 1.07, right? If we follow the rule, and get minus 3.44 volts. And we know that if you have a negative overall electro potential, your reaction is not feasible. Hopefully that made sense. I think I may probably confuse people here a lot. Hopefully I didn't confuse you. If I confused you here, leave a comment in the video and I'll try and re-explain it to you. I thought I was making sense there, but I think I may have overcomplicated it there. But leave a comment in the video that I can, and hopefully I can correct that and make it easy for you to explain later on. All right, so the next one I'm talking about is drawing cells and predicting reactions. So there's a standard shorthand way of drawing electrochemical cells in chemistry. So I shouldn't say shorthand way, the shorthand way of drawing cells is like this, right? So instead of doing this is just the overall equation. Or instead of doing two half equations, what we can just do is this. This is the way that we represent, we call it this the conventional method. That's the actual way of saying it. So I'll probably write here. The conventional representation. All that. Yes. So what it is, you have the reduced form. So what's being, you have the oxidation on your left hand side and your reduction on your right hand side, which means that in between, in the middle, you're always going to get, so this reaction here from Mg to Mg2 plus is your oxidation, right? And from, I just want to show here, and your reduction is going to be on your right hand side, which means that your your oxidized form, your ions out, you're always gonna have ions in the middle, always in the middle, and your let's say you're always gonna have ions. I mean, you could have ions on your left hand side and your right side, but your oxidized form, both oxidized forms are always gonna be in the middle, right? Now, I want to write this here because you can probably see some lines here that don't make any sense. So, the standard shorthand way of writing electrochemical cells, the more negative the more negative potentials go on the left, or technically the right. The more positive potentials go on the right. Yeah. So the negative potentials go on the left. The more positive potentials go on the right. What they mean here is what they mean here is oxidation, reduction. Talking about electron potentials. The oxidized forms will be in the center, and different couples are split by double vertical lines that indicate a salt bridge. So this double line in the middle represents the salt bridge. The lines here represent a different state of matter, so that could be the electrode. So if we have an electrode, this where there's going to be two different states of matter, because this is going to be Mg2 plus in your solution, and this is Mg solid on the electrode. And the line here represents that there's two different states of matter, and that's representing the electrode, right? But there are instances where there's no change in state of matter. So, for example, platinum is H2 gas to aqueous. There is a state of matter, and you obviously know that platinum electrode is used here. It's not part of the reaction. We still say platinum, H2 gas. And this is very important that you understand this here, because this can be used to understand the so this part here in particular is standard hydrogen electrode. Understanding that it's going from H2 to H plus gas here. That's more going to be that's your oxidation pathway, really. That's your oxidation pathway. It depends on what type of reaction you're doing, right? But it's understanding that the platinum is the one that's being used as the electrode here, but it's not involved in the reaction. It's just used as the electrode. The H2 and the AQ and the H plus are the two different. Well, H2 is in the gas form and H plus is in the aqueous form in solution, right? But if we're going to here, right? This is just an example here, right? This is just an example, right? But SN2 plus to S plus aqueous, this is a reduction process, right? But there's no change in matter. It's just the platinum electrode is used here because there's no change in matter. We're still forming SN2 plus is being reduced, but it's going from SN2 plus to SN plus. So we use a comma to represent when there's no change in state of matter, right? And when there's no change in matter, remember, we're not trying to change the state, sorry. when we're reducing something, oxidizing something where it's not going to be no change to the state of matter, we still need a metal there to help with the reduction or oxidation process. And therefore, we'd use platinum because remember, platinum is a very good conductor of electricity, but it's very inert. It doesn't get involved in the reaction. I said that in the previous video, so if you want to understand that, go to that video. Now, predicting cell reactions. Now, we can use standard cell potentials to predict whether or not a reaction is feasible. If the standard cell potential, as I said before, is positive, the reaction is feasible. If the standard cell potential is negative, the reaction is not feasible. That's it for the content. Hopefully I haven't spoken for too long. If not, then I'll split this into 2 videos. But the next part is me going through some exam style questions. So I'm gonna have me guys look through it. This is what the questions are going to be like. Hopefully I gave you enough information to help you answer some of these questions. So I'm just going through it like this so you can, when you do answer it, you can come back to it. It's 12 marks, right? If you struggle on, I want you to try and do them. If you can't, if there's a couple of things in that you can't do, as I said, I'm going to be going through it. So I'll pause the video now and try and answer the question. All right. So I'm going to put this timer up here for 12 minutes. Right. I'm going to put on my watch as well so I can have a timer that I can see my watch as well. I'm going to be trying, now my aim for this isn't to go through it in the time. I put the time in so I can try and do it, but I'm going to try and explain to you. I can do this within 10 minutes, to be honest with you, but it's just me for explain what's going on mostly if you can't understand what's going on. But yeah, if you don't have any, if you're still concerned about or didn't understand something, leave a comment in the comment section, and I'll try to answer it for you. So, the table here shows some standard electropotential data. Use data in the table to deduce a species that is the best oxidizing agent. Best oxidizing agent is the one that's strongly reduced. Strongly reduced, and that's more likely to be Cl2 because it has the highest electropotential and it's going to be reduced. So yes, write the conventional representation of a cell used to measure the standard electropotential for the conversion of tin to tin. So from tin 2 plus to tin, so from here to here, that's a reduction. The standard electropotential, so it involves platinum as well. So first of all, SN2 plus equals, wait, no, it must mean that platinum is being oxidized. If we're trying to do the standard electropotential for the conversion of tin 2 plus to tin, H2 H plus, yes, SN2 plus. I've got to show I have to show the state of matter. Okay, a cell is made by connecting 2 half cells with a salt bridge. One half cell consists of a silver in a solution of silver nitrate solution, and the other consists of tin in a solution of tin 2 nitrate solution. Calculate the EMF of the cell and write a half equation for the reaction that occurs at the negative electrode. So the EMF of the cell also is between silver, nitrate, and... Okay, so the nitrate is just the spectator ion that we don't care about. So this and tin, there's only one type of tin, so it's these two here. That's that, and that's that. So it's really just 0.8 minus 0.14, which is equal to 0.94 volts. Okay, write the half equation for the reaction at the negative electrode. So it's going to be the one that's going to be oxidized. So this direction. that's more negative, so it's more going to be more oxidized. So tin solid. SN2 plus aqueous plus 2 electrons. Use data from table above to write the equation for the reaction of silver 1 ions with iron 2 plus ions. So silver 1 ions and iron 2 plus. Yeah, it makes sense. It's going to be between this and this, this and this. So that's more likely to go in this direction. This is more likely to go in this direction. Yeah, that's it. It's just Ag plus aqueous plus Fe2 plus aqueous. You should be able to spot this. If you can't spot it instantly, but you can see what I'm trying to do here. They're already balanced, so we can just still go like that straight away. Ag solid plus Fe3 plus. How much time have I got left? 7 minutes. Okay, so I've done well for time there. Still got a minute extra. Fuel cells are increasingly important energy source for vehicles. Standard electric potentials are used in understanding some familiar chemical reactions, including those in fuel cells. The following table contains some standard electric potentials. The data. Okay. A salt bridge was used in the cell to measure the electric potential. Explain the function. Okay, explain the function of a salt bridge. Is to allow the free movement. Don't like the way I wrote that there. Allow the free movement of ions in the ionic solution in the between the solution. So allow the free movement of ions in the ionic solution to move between the cells, to move between each half cell via a salt bridge. Solution via a salt bridge to maintain. Now you can do it as bullet points here, and to maintain charge balance. Use data from the table above to deduce the halide ion that is the weakest reducing agent. Okay, so weakest reducing agent, I like to think about it as like the strongest. So I like to think about this as the strongest oxidizing agent, but it's not, and I'll come back to why. I'll tell you why I think so. I like to think about it as if it's the weakest reducing agent, I like to think about it as the strongest oxidizing agent, but it's not at the same time. I'll say why. If it's the strongest oxidizing agent, it's the one that's most likely to be reduced, so strongly reduced, right? So the one that's strongly reduced is F2, but they said weakest reducing agent, so it means it's it's the one that's going to be, if it's the weakest reducing agent, it has to be getting, it has to be getting reduced. So it has to be acting as a reducing agent, so it has to be oxidized. So the one that's least likely to be oxidized, this is the least likely oxidation to happen because it's so positive. the least likely oxidation to happen is F minus, getting oxidized to F2. So I say F minus. Use data from the table to justify why sulfate ions shouldn't be capable of oxidizing bromide ions. Sulfate and bromide ions. So sulfate's here, bromide's here, because the electron potential of SO42 minus is lower than the electron potential of Br2. So the electron potential of SO42 minus, and you can represent it like this, is lower than the electron potential of, sorry. Yeah, you can just, that in itself is enough to say what you mean. The electron potential of SO42 minus is lower than the electron potential of Br2. So SO42 minus is, I say, more likely that's nothing to say anything really. That in itself is enough. I don't have to say anything more. That in itself is enough. It's only 1 mark anyway. That's in itself and it's enough. Use data from the table to calculate a value for the EMF of a hydrogen oxygen fuel cell operating under alkaline conditions. So that's the one of them. So this is one of them. No, that's an acidic condition. So no. This one here. So yeah. So it's gonna be between this one here and this one here. And how much time have I got left? 2 minutes. So I don't want to spend too much time doing this one here. It's gonna be 0.4 minus 0.83. So 0.4 minus 0.83, which is 1.23. I could just do that in my head. 0.83 plus 0. Just 0.23 volts. So also 1.23 volts, sorry. Okay, and calculate, following cell has EMF of 0.46 plus 0.46 volts. Which statement is most correct by the operation of the cell? The metallic copper is oxidized by Ag. It is. Yeah, it is. This is being oxidized. The metallic copper is being oxidized to Ag by Ag plus. Yeah, and this is being reduced. Yeah, I can just say it's that directly. Right. Yes, I've got 1 minute 5 seconds left spare. Now you can use that 1 minute 5 seconds to look over your question and see anything that's wrong. I could just add to this here to maintain charge balance between the half cells. And that's it. Alright, and that's it. I'm quite confident by the rest of this. Just make sure that's done. I did do that. I did. Yep. Alright, so that should be, the timer should be coming up so soon. Done. Alright, now let's go through the mark scheme here. Okay, so we know that this is going to be CO2. Okay, so this is CO2. I'm looking at the mark scheme here. Platinum, H2, H plus. Oh, you didn't have to put the. Oh, it says ignore state symbols. So I guess for some of them, you have to put the state symbols. But I always put the state symbols just in case, but I think usually they would say, in your question, they would usually just say, and make sure to include state symbols if it is that type of question. But either way, they would just ignore it. So don't worry about they won't take away marks for you adding state symbols to your question. 0.94 volts. SN solid. yeah, I guess I don't have to write state unless they specifically state. You don't have to actually put your state symbols. My bad, but I always put them down because just in case. But yeah, I guess for some questions you don't have to put them down unless they specifically state it. Yes, that's 6 out of 6. No central C. 10. The ions in the ionic substance in the salt bridge move through the salt bridge. That allow free movement of ions via the salt bridge. I said so. I can comparing the ions in the ionic substance in the salt bridge move through the salt bridge to allow the free movement of the ions in the ionic substance to move between the half cells via a salt bridge. I'd give myself a mark for that, man. There's probably you might say that's something that's wrong. There's probably someone reading this saying that's completely wrong, but I don't believe. I mean, I've said the same thing, really, haven't I? If there's a teacher watching this saying that's completely wrong, you can't accept that, then fair enough, listen to them. But I think that's the same thing. To maintain charge balance, yes, to maintain charge balance, definitely that. I think that's that. F minus, yep. Electrode potential of SO4. Yeah, electric potential of SO4 2 minus is greater than the electric potential of Br2. Or you can say the electric potential of SO2 is greater than the electric potential of Br minus, and that's literally it. You can express it in words, that's fine. If you want to say, you can literally say the same thing but in words. For example, the electric potential of sulfate ions or sulfur dioxide is less than that of bromine or bromide. So that's that. 1.23 volts, yes. And then 11 was A. There you go. And that's it. Hopefully this video was helpful to you. And yeah, hopefully it wasn't too long.